Hey, welcome back. All right, this is our last section in our thermochemistry that we're going to be talking about. We'll go ahead and share here so that we can see what's going on. So, enthalpy, that's what we're going to be talking about now. Now, the enthalpy of chemical reactions. If we can keep the volume constant, the change in internal energy is only related to the change in heat. So if our pressure doesn't change, if our volume doesn't change, then delta U, that potential energy, is equal to Q minus P delta V. Q is the heat transfer. P delta V is our work for that system. And if P delta V is 0, then we only have Q, which is the heat change at constant volume. Okay. Since this is nearly impossible to do, we now define a new function of a system called enthalpy. Okay. And enthalpy, H, is equal to the U, that potential energy, plus P times V, where P is the pressure, V is the volume, U is that internal energy, and U is the enthalpy. H is the enthalpy. All have energy units. These are all energy units. Now, U, P, and V are all state functions. So delta H is also a state function because it's made from state functions. So state functions, awesome. If we hold pressure constant, then we get the change in enthalpy is equal to that change in internal energy plus pressure times the change in volume. Okay. So that's cool. Awesome. Since most chemical reactions are constant pressure, we can equate the following. The delta H is equal to the H for the products minus the H for the reactants. We'll get back to what that means in a few minutes. Now, if delta H is positive, the reaction is endothermic. So I'm taking in energy from the surroundings. Delta H is positive. Okay. Negative delta H is exothermic. So again, my system is losing that enthalpy and it's going out to our system. Here, heat is a reactant. Here, heat is a product. Okay, so just like we talked about with Le Chatelier's principle, so if we change the temperature and we add heat to this thing, if it's an endothermic reaction, that makes that reaction go forward. Right? If it's an exothermic reaction and we add heat to this, then it makes it go backward because that's not a favorable situation. Okay, so that's important for us to be able to look at. We can see that effect from Le Chatelier's principle. Thermochemical equations show both the mass relationships and the enthalpy. So let's take a look at this. CH4 gas plus 2O2 gas goes to 2CO2 gas plus 2H2O. That has an enthalpy change of 88.0 kilojoules per mole. Okay, awesome. So much fun. If we could talk about H2O solid going to H2O liquid, that delta H, that enthalpy change, is 6.1 kilojoules per mole because it takes energy to go from the solid to the liquid. But if we talk about that for 2 moles rather than 1 mole, we have 2 H2O solid going to 2 H2O liquid. That delta H is 12 kilojoules per mole. Okay, so this is dependent on the stoichiometry. So remember, we talked about the fact that our Ks, our equilibrium constants, are dependent on stoichiometry because that's how we look at the exponents in those expressions, right? So it depends on the stoichiometry. When we talked about standard reduction potential, that does not depend on the stoichiometry, okay? But when we looked at reaction rates, that's dependent on our stoichiometry for elementary reactions, but only for elementary reactions, okay? Now, if I want to talk about H2O liquid going to H2O solid, that's related to this expression right here, but it's the reverse process. So instead of taking in heat, we're going to be losing that heat. So we lose that negative 6.01 kilojoules per mole, okay? So those values are dependent on the physical state and the stoichiometry. So if I multiply my equation by 2, the value of delta H is doubled. And if I reverse the reaction, the value of delta H changes sign. Okay, so those are some important things that we need to be able to remember when we talk about the enthalpies. Okay, some practice. So what you'll see a lot of times is that there are standard enthalpies of formation of some inorganic substances at 25 degrees. Now, standard enthalpy of formation is how much energy it takes to make that thing at 1 atmosphere, 25 degrees, under normal conditions, 1 mole of it being made from things in their initial states. Okay, so if we're talking about making AgCl, we have to start from Ag solid and Cl2 gas. Okay, this is how much energy it takes to make AgCl from under those conditions. A couple of things that you need to note that may not be obvious to you, so we're pointing them out. The formation of 4 moles of Al2O3 solid can be found by looking at the formation. So Al2O3 solid has this value right here of negative 1669.8, and that's for 1 mole. So the units on that, and actually I'm going to do it that way, and this is kilojoules per mole. Okay, if I want to do it for 4 moles, then I can do my happy math, multiply that by 4 times that negative 1669.8, and that gives me, and actually, hold on 2 seconds. Sorry, I want to take my calculator out of scientific notation. That's negative 6679.2 kilojoules. So that per mole has gone because we now know that this is for a 4-mole process. Okay, so that's how that works. Why is the heat of formation, F2 gas, 0? So if I look at F2 gas, it says 0. Why would that be 0? Because that's F2 in its natural form. That's how it exists. So the energy needed to be in its natural form is 0. So that's why. So anything that's in its natural form, how it exists in nature, is going to be listed as 0. What is the formation of H gas? Not the same as H2 gas. So if we look at H2 gas, that has a value of 0, right? And that makes sense to us because that's how it exists in nature. But H is not how it exists in nature. And so that has a value of 218.2 kilojoules per mole. And that's how much energy it takes to break that H-H bond. So to get it from H2 to H, that's how much energy we need to put in to make that happen. Okay, so that's what we're talking about there. Right? It's important that we understand that. Now, we can also talk about the formation of HF from H gas and F2 gas. Okay, so instead of looking at the formation of HF gas from, and actually let me do it this way, apologize. So we could talk about H2 gas plus F2 gas going to give me HF. And if I do that, then I've formed it from the components that I would expect in their natural state, these two guys right here. And so that would be a delta H of formation, standard formation for HF, which is listed as the negative 268.61. But it's not going to be the same value if I look at the formation of HF from H gas and F2 gas. Because in order to do that process, I first have to break the H2 to give me 2H gas. And then I have to take those 2 H's and use them in this process. So I would have to take 2H gas plus F2 going to HF. And so that mathematics is not going to be the same as what we talked about previously. So how would I find that value? Well, that's interesting. We talked about this a couple of slides ago, and I said we'd come back to it. So what I said was that the H for the products minus the H for the reactants is what we're looking for. Okay, awesome. So let's see what that looks like right here. So we know that the H for this product, this HF, is this value that's given right here. We found that from the table. That's right here in my table. Where's my? There, right there, negative 268.61. So negative 268.61 is that product. And then my reactants for the F2, that's going to be 0. Remember the F2 is right here. That one's going to be 0. So 0 plus the energy that it takes to make the H from the H2. And again, we listed that. That was 218.2, right? But when I make that one H, Okay, that's a different energy than 2 H's. So I have to take and multiply that by 2, 218.2. And so that's the mathematics that I'm looking at for how much energy it's going to take to form HF from those H's as opposed to H2. So if I do that math, negative 268.61 minus 0 plus 2 times 218.2, and that gives me negative 705.01. And that, again, is kilojoules. Okay? So that's how we find that. So the formation of AlCl from Al solid and Cl2 solid. So I have AlCl listed here as negative 127.04. My Al solid is 0. My Cl2 gas is 0. And so my Al solid formation is just the negative 127.04, because when I subtract my reactants, that doesn't change anything. So that's the value that I'm looking at for the negative AlCl. So that's negative 127.04. This is negative 705.01. Okay. Just thought it might make it easier if I actually put those answers with the questions that they went with. Sorry. How much energy does it take to change from a rhombic form of sulfur to a monoclinic form? Okay, so let's talk about that for a second. So you may remember once upon a time in 110, we talked about different crystal structures. And there are lots of different names for crystal structures. Sulfur is something that forms into many different crystal structures, one of which is called rhombic, one of which is called monoclinic. So the rhombic form is the one that it naturally forms. That's the way we find it in nature. So that has an energy of 0. You'll see that right here, this S rhombic is 0. The S monoclinic, on the other hand, is 0.30. So it takes 0.30 kilojoules per mole to turn this from a rhombic state to a monoclinic state. So we've shifted around the order in which those things occur in that crystal, and that's what we get from that particular substance. Okay? So that's how we can use that delta H. Awesome, that was fun. Now, comparison of delta H and delta U. Since there is work done if the volume changes in a reaction, the internal energy and enthalpy are not always the same. They're not always. The values are very similar, but differ in the amount of work done by the change in volume. So my delta U, that potential energy, is equal to the enthalpy, that delta H, minus RT delta N. So R is my gas constant, T is the temperature, and delta N is the change in number of moles of gas. Okay? Since the change in volume in most reactions comes from a change in number of moles of gas present, we can rewrite our relationship that way. Okay, so that is a way that we can look between that potential energy and the enthalpy if we need to do so. I'm not going to ask you to do that, but that is something that we can do. Okay. Questions, comments, problems so far? Hopefully not. Let's keep going. So some sample calculations. Given some things that we have talked about, what can we do? So given the following information, calculate the heat evolved when 87.9 grams of SO2 is converted to SO3. If I look at this reaction, 2SO2 plus O2 gas goes to 2SO3 gas. Delta H for that is negative 198.2 kilojoules per mole. So it's exothermic. We're giving off energy when this process happens. This amount that we have is for the formation of 2 moles of SO3. 87.9, I don't know if that's a mole or not. I don't exactly know how much that is, but I can take that 87.9 grams and divide it by the molecular weight of the SO2 to tell me how many moles that is. So that would convert this to moles. And once I know how many moles that is, I can multiply this by that heat, the negative 198.2 kilojoules per mole. I did not do that right. Holy mackerel. Okay, oops. Oh, and it's kilojoules per 2 moles of SO2. That is right. So this is how much energy there is when I make 2 moles of SO2, because there's right there, 2 SO2. Okay, so that's why there's a 2 down here. And so that means that when I only have that amount of it, then that's the enthalpy that I'm going to be looking at for that. So sorry, I hope that makes sense. All right. Now, if I wanted to look to calculate the change in internal energy when 2 moles of CO are converted to 2 moles of CO2 at 1 atmosphere at 25 degrees, we'd be talking about 2 CO gas plus O2 gas. We need 2 CO2 gas. That has a delta H that's been calculated. We'll figure out how to calculate it later, of negative 566.0 kilojoules per mole. If I want to look at the potential energy, that's this delta U. So that's equal to the delta H, which is this value right here, minus RT times delta N. Now remember, delta N is products minus reactants. So I have 2 product molecules minus 2 product moles minus 2 product moles on the CO plus 2 reactant moles on the CO plus 1 reactant mole on the O2. So that gives me a net of negative 1 moles. Okay. So we've gone down from 3 to 2, so that's negative 1. So I can take and put into my delta U equation that delta H, a negative 566.0 kilojoules per mole minus the 8.314 joules per Kelvin mole. That's my R. And notice that's in joules, not kilojoules. Convert that to kilojoules, because I need to do that, times the 298 Kelvin, times the negative 1, which is my delta N, and that gives me this value right here. So that would be my internal energy for that particular problem. If you were asked to calculate, that's exactly what you would do. Okay? Is there anything else we want to talk about? A couple other things. So 2 H2O solid goes to 2 H2O liquid, and that's 12.0 kilojoules per mole. We talked about that. How much energy is required to take 42.42 grams of water from solid to liquid? Okay, well, I have 42.42 grams of H2O. And I know that each H2O, if I remember correctly, 18.02 grams of H2O per mole of H2O. So that gets me to moles of H2O. I know, I can look at it when I'm looking at it. I know that for 2 moles of H2O, the energy involved in this conversion is 12.0 kilojoules per mole. And it actually doesn't matter if I'm talking about solid or liquid because there's the same number of moles, so we're okay there. We are talking about the solid, so there is that. And that will tell me how much energy I require to convert this amount of material. So that 42.42 divided by the 18.02 tells me that I'm converting 2.35 moles, which I then multiply by 12 and divide by 2. And that tells me that it's 14.12. And of course, that's kilojoules. Okay. Awesome. That was fun. Questions about that? Cool. Given CH4 plus O2 goes to CO2 gas, what is the energy in 68.32 grams of CH4 from CO2, assuming that a similar amount of O2 gas is formed? Okay. So if we have enough O2, then we should be fine doing this. So I have 68.32 grams of CH4, molecular weight of CH4, and I'm not going to pull it back over here, assuming I can find it, of course. Oh, I am. 16.04. And then this was, it's helpful if I actually show you what I'm looking at. This was 88 kilojoules per mole, and that is for 1 mole of CH4. And that tells me that I am looking at 68.32 divided by 16.4 times 88. 374.82 kilojoules. Okay. Awesome. That was fun. What is the amount of energy? What is the amount of energy if 42.4, oh wait, sorry, I skipped one. What is the amount of energy to form 2.5 moles of CO2? Well, so this is how much energy it takes to form 1 mole at 88 kilojoules per mole. So 88 kilojoules per mole of CO2, because that's what was in my balanced equation. And I want to make 2.5 moles. (88 times 2.5), and that's 220 kilojoules. Okay. And what is the amount of energy 42.42 grams of CH4 and 32.7 grams of O2 are mixed to make this? Well, I already have something for the 42.42, right? That's a calculation there. Now, I know that 42.42 divided by that 18, no, wrong thing. Okay. So this is actually not the right one because this was for H2O. So now we're talking about 42.42 grams of CH4, 16.04 grams of CH4 per mole of CH4. And of course, if we're talking about the number of moles of CH4 and the number of moles of O2, they're both 1 to 1. So I need 1 mole of CH4 to make 1 mole of CO2. I need 1 mole of O2 to make 1 mole of CO2. So awesome possum, 42.42 divided by 16.04 tells me that I have 2.645 moles of CH4. Now I want to compare that to the 32.7 grams of O2 per mole O2, and the molecular weight of O2 is 16, so that should be roughly 32. And if I look at my Happy Lentech, just to make sure that we get 32. So 32.7 divided by 32 gives me 1.02. So that means that I don't have enough of one of those materials. One of those materials is limiting, right? And what it says is, what is the amount of energy if this amount are mixed to make CO2? What's my limiting reagent? My limiting reagent is this O2 because I have less moles of that. I need 1 mole of O2 to make CO2. I need 1 mole of CH4 to make CO2. So that's my limiting reagent. How do I know? Because I did this calculation. That's how I know. And how much CO2 is made in this reaction? I make 1.02 moles of O2, 1 mole of O2, 1 mole of CO2 gives me 1.02 moles CO2. And of course, if I wanted to convert that to grams, I could do that. I would need to multiply by the molecular weight, which is 44. And that's 44.96 moles CO2 that are actually made. Now, if I know that the amount of energy is based on the amount of O2 that I have, I take that 32.7 grams divided by the 32, and then I multiply that. So 32, I'm sorry, I don't have a lot of space. Unfortunately, won't let me scroll up anymore. So So I'm taking this calculation that gave me the number of moles of O2. And then I'm looking at how much energy do we have kilojoules per mole wise. I have 88.0 kilojoules per mole. So that 1.02 times 88 gives me 89.76 kilojoules. Okay. So yay, that was fun. So this brings back memories, right? Because it's a limiting reagent. We have to do the calculation, see which one is the one that actually limits this, blah, 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 blah. That is what we're dealing with here. Okay, so this is absolutely no different than what we talked about before, except now that we're adding how much energy is required to do this kind of reaction. Okay. Awesome possum. Questions, comments, problems about that? Really, it's not going to listen to me. I'm this excited. Questions, comments, problems? Hopefully none so far. Let's talk about a couple of other things. So what is a state function again? State function does not depend on path. Initial and final states only. Now, name state function. U, P, V, and H. So we said U, P, V at the beginning. H also, yay. That's an isolated system. Isolated. That was the one that didn't transfer matter or energy. So exothermic gives off heat. Delta H is negative. Heat is a reactant. Sorry, not a reactant. Heat is a product here. Endothermic takes in heat. Delta H is positive, and that is a reactant. Okay. The combustion of methane, CH4, releases 890.4 kilojoules per mole of heat. In the reaction, CO2 plus H2O gives CH4 plus 2O2. Okay, so that's to make the methane. Right? How much energy is given off when 2 moles of CH4 are burned? Okay, so wait, I want to look at when CH4 burns. That's not the reaction that I have here, because this is the reaction to make the methane. So I need to reverse this. And so what I'm going to be looking at is CH4 plus 2O2 going to CO2 plus 2H2O. And of course, the delta H for that is going to be the negative of what I had before, 890.4 kilojoules per mole, which makes sense because it should be giving off energy when I am combusting it. How much energy is released when 22.4 grams of methane are burned? Okay. 22.4 grams CH4. Methane. I think that I calculated this before. I'm pretty sure I did. Come on. 16.04 was the mass that I calculated for that. 16.04 grams of CH4, mole of CH4. But I'm looking at 890.4 kilojoules per mole of CH4. And that means that if I only have 22.4 grams, 22.4 divided by 16.04 tells me I only have 1.39 moles. And multiply that by the 890.4. And that gives me negative 1243.4 kilojoules that are released. Okay, and it's negative, so it's exothermic. If you make 45 grams of methane from carbon dioxide and water, how much heat is required to do that? So instead, we're looking at the other reaction, so going the opposite way. We're taking 45.0 grams of methane that I want to make I still need to divide that by 16.04 grams of CH4 per mole of CH4. But this time, since I have to make the CH4 rather than consume it, this is going to be a positive 890.4 kilojoules per mole. And that gives me 45 divided by 16.04 times 890.4, 2498 kilojoules are required to do that. Cool, that was fun. What is the heat of formation for this reaction if 2NO gas plus O2 goes to 2NO2 if delta H for NO is 90 kilojoules per mole and NO2 is 34 kilojoules per mole? Okay, what is the heat of reaction if 1 mole of NO is made from NO2? Okay, so I want to know what's the heat of formation for this thing if the delta H for NO is 90 kilojoules, and the delta for NO2 is 34 kilojoules. So I'm going to write that right here. 34 kilojoules there. This one here is 90 kilojoules. And of course, O2 is 0, because that's how it appears in nature, so that's 0. Now remember that if we want to do delta H, it's equal to the H for my products minus H for my reactants. So my product here, 2 moles of 34 kilojoules per mole minus 2 moles of 90 kilojoules per mole. And that's equal to 2 times 34 minus 2 times 90. Negative 112 kilojoules. Awesome. And that's for the formation of 2 moles of that particular species. Okay, awesome. What is the heat of a reaction if 1 mole of NO is made from NO2? So we divide that equation by 2 to get that. So instead of being 2NO plus O2 goes to 2NO2, we want to look at NO plus half NO2 goes to NO2. And it's equal to 1/2 of the negative 112 that I just calculated. So it's negative 112 divided by 2. Gives me negative 56 that are given off when I do that. Cool. That's fun, right? Well, awesome. So that's where we are. Do I have anything else? I'm trying to see if I have anything else. No, I don't think I did. Oh, I did say, please complete the thermochemistry in class practice. So I'm going to pause here. I'll come back. We'll talk about that thermochemistry in class practice. But for right now, we're done. If you don't feel like you need that thermochemistry or don't need to watch me do it, then that's okay. The answers are posted on D2L, but that will be available for you as well. Okay? All right. I'll talk to you guys soon. Thanks.